Okay, this is our first attempt. We're actually going live on YouTube with this, so we'll see if this actually works. It's pretty much live. I'm going to stick it up right after we're done. So in this lecture, this is kind of the last lecture. I didn't put Gram-Schmidt in there. We were already at 120 slides. So this is kind of the last lecture of new stuff, and I'm going to probably put Gram-Schmidt up separately. It's a procedure, so it's something more simple to understand. In chapter 6.1 and chapter 6, they talk about inner products. I'm not assigning homework out of this. I'm going to have you learn things by doing things through in-class assignments, rather than this section be homework and graded on a test. I am going to present the inner product differently than they do in the book. In the book, they present inner products using just Rn. So the point doesn't seem very clear, because why would you need to have all this structure for a dot product which you already know something about? So I want to make it very clear what this is all about. So the inner product is an abstraction of the dot product. So you basically start with a vector space, and now you're going to add something to it. An inner product has several properties. You're getting used to this idea. You get some abstraction which has a set of rules that you picked off from the examples that you really understood well when you were little. When you're little, back in Calc 3, you understood dot product really well, so you'd like to abstract that idea. So the first property is that the dot product has this distribution that you can take the W and basically have the distributive law applied. The second and third and fourth properties are pretty standard, that if you have a constant, that constant can be rotated around. The dot product is commutative. The most important one probably is the fourth one, that the dot product of u is going to always be a non-negative number, and the only way that you can make that 0 is if u itself is 0. And IFF means if and only if. I knew you were going to ask that.
Number 2. Yeah, what's number 2?
Number 2, I think I'm supposed to put the C in between the U and the V.
Oh, okay.
Right. So you look at these rules, you get them actually. If you go back and look in your Calc 3, in your Calc book is gigantic, because you don't have just the examples and how the procedures of how to do things. You also have these rules that come with every single thing. If you go back and look at simple things like taking the derivative, back when you took the derivative, they have a whole section on the linearity of the derivative. The fact that taking a derivative is a linear transformation. At the time when you're taking it, it looks like information that doesn't need to be there. And when professors actually present that, it probably looks like professors are presenting material that I don't really need to know. It's kind of because we are taught that structure is very important, that someone can't omit it out of a book. When someone omits it out of a book, there's a large outcry. There's a book that was written by, I think the author's name is Hughes Hallett. It was really popular back 10, 15 years ago, where she didn't write down all those structural things, but had more focus on the problems and deeper kinds of problems, where you think deeper about the calculus. And the outcry there is she's got to have epsilons and deltas. I think mathematicians had a backlash towards that and said, you know, you've got to have the structure. It's wrong otherwise. We're very big on being right. We have to have everything be exactly correct as we write it. So the example that you have is the dot product on Rn. So I'm going to do something different. Your book has plenty of examples about Rn. I'm going to show you something different so you can actually think about what this means. So the example I'm going to give you is a different vector space. And I already gave you some examples like this where you have a different kind of looking vector space. And in this vector space, I have functions where the domain of those functions belong to 0, 1. Those functions are real valued. And the criteria is that if I integrate the square of that function, that square of that function is going to have an integral that's of finite value. Now that's a lengthy definition for a set. So what's in there? Well, f of x equals e to the x, not e to the x squared, is in V. E to the x squared is also in there. How do I know that? Because what does the integral represent? That's right, you got to answer really well because you know you're on YouTube. It's the area under the curve, and if I draw e to the x, or e to the x squared, that area that's under that curve is a finite area. I can see it. I only need my eyeballs to know that that's a finite area. By the way, I chose this function because there's no closed form solution to this. This is something that maybe your professors talked about in Calc 2, but e to the x squared has no antiderivative that you can write down. But it does have a finite area, you can see it. So you can estimate this by using triangles underneath the curve or trapezoidal rule. You easily estimate this. So another example, what if we take 1 over x? Is that in V? Well, for it to be in V, that means I have to square it. There's like lots of integrals in this lecture, actually. You have to square it, take the integral, and show that that integral has finite value. Well, when I square it and take the integral, I have a problem at 0. 1 over x squared at 0 has an asymptote. So back to the end of Calc 2 when you did improper integrals, this is an improper integral. You have to start from epsilon to 1 and take the limit as epsilon approaches 0 from the right. And what I get when I take the antiderivative and do all the calculations is basically that this integral is not finite. I get an infinite value. So this example is not in V. So now I have an example of something that's in there, and I have an example of something that's not in there. I have a better feel for what that set is. So there we go. Now, there's an inner product on this weird vector space. And that inner product, that dot product, is that the dot product of two functions, f and g, is the integral of f and g on 0, 1. That definition satisfies those 4 rules that I showed you on previous slides. So what does that inner product, what does the inner product in Rn tell you? There's, you walk away from your class in Calc 3 and you ask students a question, they always get this one right. What does the dot product tell you from Calc 3? What did you use it for? That's right. They're in Calc 3, so. So if you take the dot product of 2 vectors in R3 and their dot product ends up being 0, then you know that those 2 vectors are perpendicular, or the graduate word is orthogonal, right? And do you remember anything else? If you're a physics major, I don't think we have any physics majors in here. It tells you actually more than that. The dot product of 2 vectors, there's a formula. You're getting there. The dot product between 2 vectors gives you the angle between those 2 vectors. So there's a formula that translates one to the other. And the important thing that you focused on is that if it's 0, then the angle between the 2 vectors it's going to be perpendicular. So it gives you the angles between vectors, and it also tells you when 2 vectors are orthogonal. That's the important take-home message that most students who graduate out of Calc 3 get. I don't know what about the students who don't graduate out of Calc 3 because they didn't pass it. But I just do know that no matter what stage of after Calc 3, when I've asked that question, most of the class has resounded with the dot product equals 0 means that they're perpendicular. So something was retained. So if I have u dot v equals 0, it means that it's perpendicular. I'm just rewriting what we already just echoed in here. So for example, I can take 2 vectors in R2. I can graph them. I can actually see it, that they're perpendicular, even with my crazy looking graphs. But I can also calculate it directly from the dot product, and it turns out that the dot product of these 2 vectors is 0. Likewise, if you take 2 vectors in R3, it's a little bit harder to draw this. You need the 3-dimensional plane. I always get this messed up. The xy plane is on the floor, the z is the elevator going up and down. The z should really be coming out. And that's the first vector u drawn out. It's shooting up in the air like this.
Does it matter which way x and y go?
Physicists, and I think physicists do it right. This is the only thing I think physicists do right. This is going to be live on YouTube. Right. So the xy plane is, for physicists, is the wall. So it's like your usual Cartesian plane, and the z is the 3rd dimension that comes out to you, right? That makes more sense. But mathematicians are topsy-turvy. We have the 3rd dimension going up and down. We took the plane, which you're familiar with, just to confuse you, and we put it down on the floor.
Isn't x and y for math?
X is this way and Y is that? Did I get that wrong? Got it right. Yeah, I want to do it the application way. I want the z coming out at me, but. So I can still see these 2 vectors, and I can imagine that they're perpendicular. I can see it. And I can calculate it too. Now I have two vectors in R4. I had a professor named Dr. Rotruba for my Calc 3 class, and he said he could see it. I can't see it. And I think most physiological healthy people can't see it either. I think it's just him. So we can't see it anymore, but we can still calculate it. So you probably did this. I don't know if you did this in Calc 3, if you moved beyond 3 dimensions and talked about 4 dimensions. There are definitely 4-dimensional problems. People would say in Calc 3, well, I'm never going to use this because anything past 3 dimensions doesn't make sense. The n-body problem, n planets orbiting around, is an n-dimensional problem. So you can get real problems all the time that are going out after 3 dimensions. But here I can't see it, but I can definitely calculate it. These two vectors I would call orthogonal because their dot product is 0. So that measurement, that metric that I had in R2 and R3 still holds when I can't see it in R4. What's wild is it even holds in these weird spaces that I just showed you. So if I have that vector space V that I defined earlier with the functions, I can do it again. In this vector space, cosine pi x is perpendicular to sine pi x. How do I do that? Well, I take the dot product of cosine and sine. To do that, I take the integral of cosine and sine. That's a u substitution. The only thing I don't do today, I think, is partial fraction decomposition. Everything else I'm going to hit. 2 students in here had me for Calc 2. You know that I'll try as much as I can to get a trig function in there. So here's a trig function, and you see that if I take u to be sine pi, and I transform the limits of integration, I get the du, pop everything in. My integral now goes from 0 to 0, and I get that my solution's 0 no matter what, right? Because I'm integrating from 0 to 0. So I just checked whether Maple was working, and it got it right as well. So these integrals are correct, and that tells me that cosine is perpendicular to sine. And you use this, actually, this concept of the cosine pi x and the sine pi x being orthogonal functions. You use this in quantum mechanics, which you too, yeah, right? Are you doing something like that in there? Yeah. Right. Yeah. So Fourier series. The Fourier series is it's built on this idea that you're taking orthogonal functions, and it's like a Taylor series version with trig functions in it. How about seeing it? Well, one of these is cosine and one of these is sine, right? The red curve is cosine and the blue curve is sine. Can you see that they're orthogonal? No. There's no way to see that, right? It's out of the realm of seeing. But the calculation gives you that they are orthogonal function. Another cool thing about inner products is they give you a notion of length. You didn't think about that in Calc 3. In Calc 3, they gave you the magnitude first, right? The magnitude of a vector. And the next step was using the magnitude to get, you had the dot product, and they probably never talked about the relationship between the two. But there is, and it's kind of obvious. If you take u dot u, you get the magnitude squared. The magnitude has a square root at the top of it, right? Right, and there's no square root here, so you get them. That's the relationship. So the magnitude is always going to be the square root of the inner product of u dot u. From that, you get a notion of length. How do you measure length for the first time? When you're very little, you measure it using absolute values. Right? That's the way you first thought about absolute value. You say, what is the absolute value of -3? It's 3. It's the distance from the number on the number line from -3 to 0. So it's a distance. And then you move and graduate up to Calc 3 and you start using magnitudes. But if you want to abstract the whole notion of absolute value, what's good about absolute value? Number 1, it's never negative. It's a distance. So that's property number 1. Number 2, if you multiply by a scalar, you can scale that scalar out. And number 3, you have what's called the triangle inequality, which you don't think about that much, but you started to probably use it in Calc 3. And don't you all have to take physics? Everybody here has to take physics. Computer science doesn't have to take physics. Good, that doesn't really make sense. But in physics class, you probably used the idea of a triangle inequality because you have to compare lengths to each other. Your good old magnitude from Calc 3 does this. In advanced calculus, those students taking advanced calculus, they'll prove this, that this is actually true. But there's certainly, on the vector space I just gave you, that's the magnitude. It satisfies those 3 rules that I just gave you. So it acts like the absolute value on functions. I can take the magnitude of a function.
So that's the same thing as magnitude?
In that vector space that I assigned, right? You have to first get the vector space, then you have to get the inner product, then you get this magnitude. So the inner product, that dot product, induces the magnitude. They all look similar too, right? With squares and square roots. So I can actually calculate the length of, let's say, the cosine pi x. I just pop it into that formula. It's an integral. And your calculators can do this. I don't know why. I was sitting right next to Maple. I did it by hand. But remember this, just to remind you. Take the opportunity to remind you of those trig laws that if you have cosine squared, then you can transform it to cosine double angles. So you transform it to cosine double angles. You do the integral. And you get 1 over square root of 2. Integrals are quite a few calculations with pluses and minus signs, so I get kind of nervous, so I just check that my Maple is getting it right too. I didn't take the square root, I just integrated and make sure, and I got 1/2, so if you take the square root, you get the same thing. And your calculators will do that for you. Just tell it to integrate. In class on Monday, we're going to do this as in groups. So those of you who know how to do it on the calculator are going to show people who don't know, because even the TI-83 does it, and it's really, really important to be able to do those on your calculator. On the final, I'll give you something very specific where you have to calculate the norm of a function on the vector space I just gave you, just like I did. I'll just say find its length. Here's the vector space, here's the norm, here's the equipment that you need, do it. We'll practice in class. So you should all be able to do it via calculator. It shouldn't take that much time.
It's the only question on the PowerPoint.
Well, then I'll change the function that goes on there. Just because you have a norm, it doesn't mean it came from an inner product. It makes sense, like if you think of the easiest thing that you could do in R2, for example, if you wanted to get length, the first thing that would come to mind is probably not magnitude. That seems reasonable, right? If you wanted to abstract the idea of absolute value, just take the absolute value of each component and just add them up. Or you could take the biggest absolute value out of both components. That also will work. But this actually satisfies those 3 rules too. And it doesn't come from an inner product, because you know what the dot product is in R2. It's take the sum, right? So this doesn't come from inner product. But what's the difference? Things don't look right. They just don't look right when you start graphing things and looking at things. So for example, the unit circle. The definition of unit circle, and in fact, I was reading on the Praxis of all things. The Praxis has questions about the definition of the unit circle. The definition of the unit circle is it's the set of points that are distance 1 away from the origin. That the Praxis has that? Yeah. Do you have to take it? No. your teachers of your future children will have to take it. So distance, if you define the distance, that's the distance I'm going to use, the absolute value of this. And let's see what happens if you graph that. If you graph that, you have absolute values. In each quadrant, the whole formula will change. For example, in the first quadrant, we have the absolute value of x1 is going to be positive, and the absolute value of x2 is positive. So I get this, this formula, which is a line. Just if you want to see it with y's, it's y equals minus x plus 1. That's a line, and I can graph it. If I go to the second quadrant, however, absolute value of x1, in this second quadrant, x is negative. So the absolute value of an x would be, I'd have to negate it one more time to get the correct value. And I get a different line. I get y equals x plus 1. So I get this. Right? So then you can go to the third and fourth quadrant and draw that. And that's what the unit circle with that length looks like. It doesn't look like a circle the way we know it. Right? So that's what's not good about it. That's why they didn't talk about it with you in Calc 3. Although there's these perfectly valid abstractions of the absolute value, they weren't discussed with you because none of the physics works out. If you notice your calc classes, they're based off of physics. Almost every example you can think of is acceleration, position. So that's where calculus kind of originated. The whole concept of calculus originated from physics, and that's why you get things that jive really well with physics. In our inner product norm, this is what happens. If you just look at it and set it equal to 1, that's the formula for a circle. So if you drew it, well, that's my drawing of a circle. But you get exactly what it should look like. The circle looks like a circle. And all the other nice properties that you have, all the geometry carries over. So you have that, if you have two lengths that are perpendicular to each other, then Pythagorean's theorem holds. Leg squared plus leg squared is the hypotenuse squared. So that's not true for that other norm. It's only true for norms that came from inner products. Just let's check it out. I mean, since we're integrating, why don't we integrate further? This one I don't think I go and do all the work for, but remember that sine and cosine were perpendicular on that space V that I showed you. So let's check if Pythagorean's theorem works. Is that true? Is the integral of cosine squared plus the integral of sine squared equal to the integral of cosine plus sine squared? And the answer is, I forgot my limits to integration on that second one. All right, did I do all this? I think I did. No, I didn't. I was lazy. I just did it on a computer. I integrated each one of those, and you see I get 1/2 plus 1/2 in my sum, and the right-hand side was just 1, and you see 1/2 plus 1/2 equals 1. So they all work out. Okay, so I'm going to stop the video so that I think on YouTube you start to have trouble, right?